An electrical machine is a general term used for an electromagnetic device that is used for conversion between electrical and mechanical energy. It can be used as a generator to develop electrical energy or as a motor to develop mechanical energy. So, an electric motor is a machine that converts electrical energy into mechanical energy. It has a stationary part called stator and moving part called rotor. So, when electrical energy is supplied, the rotor rotates, thereby generating the rotational mechanical energy. And it works completely opposite to that of a generator. Electric motors can be classified into AC and DC motors, while the AC motors are further classified into induction motors or synchronous motors. And these AC motors are flexible for speed control and demand low power during start. An asynchronous motor is popularly called as induction motor. And both the types are quite different from each other. The fundamental difference between these two motors is the speed of the rotor is relative to the speed of the stator is equal for the synchronous motor. Whereas the rotor speed in induction motor is less than its synchronous speed. And this is why the induction motors are also known as asynchronous motors. And in this video, we will see the synchronous motors. In this kind of motors, the speed remains constant with varying loads and the supply current frequency is synchronized with the rotor rotation. And that's why this motor helps to drive motors at constant speed and is used in machines. So without further ado, let's get started. What's in it for you are, first we will see what is synchronous motor, next the construction of synchronous motor, and then the working principle of synchronous motor, and next up the features of synchronous motor, then the starting methods of synchronous motors, further the types of synchronous motor, in that we will see the DC excited motor and non-excited motor, also the types of non-excited motors. Next to that we will see the advantages and disadvantages of synchronous motor, and finally the applications of synchronous motor. First, what is synchronous motor? Synchronous motor is an AC motor where the rotation of the rotor or a shaft is synchronized with the frequency of the supply current. And the rotation period is exactly equal to the integral number of AC cycles. Synchronous motor is one of the most common type of three-phase motor. When three-phase electric conductors are placed in certain geometrical position, an electric field is generated. And this electric field provides a rotating magnetic field. And this rotating magnetic field rotates at certain speed called as a synchronous speed. To be more precise, a synchronous motor refers to an AC motor that runs at synchronous speed. Synchronous motor is mainly consisting of two parts, one is rotor and other is stator. The stator is the unmovable part and the rotor is the movable part of synchronous motor. The synchronous motor uses a stator just like an induction motor to generate rotating magnetic field. The rotor of a synchronous motor is made up of a permanent magnet coils excited by a DC supply. When AC supply is given to the stator, a rotating magnetic field is produced. The rotor has poles having different polarities. When this rotor magnetic field interacts with the stator RMF, due to its different polarities, the stator RMF and the rotor magnetic field locks. Since RMF is moving at synchronous speed, the rotor starts to rotate at synchronous speed. So they are called synchronous motors or constant speed motors. The synchronous motor is structurally similar to the alternator or a synchronous generator. That is, it can be operated as a synchronous generator or alternator without changing the rating or design. That is, when the machine converts the input electrical power into output mechanical power, it is known as synchronous motor. And when the same machine converts the input mechanical power into output electrical power, it is known as synchronous generator or alternator. The synchronous motor is a fixed speed motor because it has only one speed, which is known as synchronous speed. And this speed is synchronized with the supply frequency. And the synchronous speed is given by n suffix s is equal to 120 f by p, where n suffix s is the synchronous speed, and f is supply frequency, and p is number of poles. And note that the number of poles depends on the design of the motor and it cannot be changed during the operation. Therefore, the speed of the synchronous motor only varies with the supply frequency. And next, let's see the construction of synchronous motor. Talking about the structure of synchronous motor, it is similar to that of other motors. Stator and rotor are the main parts of synchronous motor, while a frame is the cover, and both stator and rotor make up the electric and magnetic circuitry of the synchronous motor. The main components of the motor are stator, rotor, exciter, and frame. As I said earlier, the construction of synchronous motor is similar to that of an alternator or synchronous generator, and it differs from an asynchronous or induction motor based on its rotor design. Now let's discuss the main parts of synchronous motor. First, the stator. It is the stationary part of a motor. Just like an induction motor, the stator core is made up of thin laminated sheets of steel or cast iron of good magnetic quality to reduce the hysteresis and eddy current loss. The stator has an axial slot inside in which three-phase stator winding is placed, and it is called as an armature winding. The stator's armature winding is supplied with three-phase power through its input terminal, and it is responsible for generating the rotating magnetic field. Next, rotor. Rotor is the rotating part of a synchronous machine, and it has a cylindrical shape that holds the field winding. The rotor incorporates with the field winding, which is supplied with DC through slip rings, and it is responsible for generating the magnetic field. To be more simple, it is a rod-like type. It is excited by DC source, and the rotor rotating speed is same as the speed of the magnetic field. There are three types of rotor construction in synchronous motors: salient pole rotor, non-salient pole rotor or cylindrical rotor, and permanent magnet rotor. The term salient means pointing outward. In this type, the poles protrude from the rotor surface. Here, the rotor core is made up of a laminated steel sheet for reduction in hysteresis and eddy current. The field windings are wound around each pole. The salient pole rotor has a large diameter and short axial length. The air gap in the salient pole rotor is non-uniform, and the poles are projecting in outward direction to the rotor surface. The poles are laminated by silicon steel and carry the field winding, and the pole faces are generally provided with slots which provide support for squirrel cage winding. The damper bars are short-circuited at both ends by the copper rings. The working of damper winding primarily provides the starting torque and restricts hunting, that is the unwanted noise and vibration of a machine in a synchronous motor. Talking about the characteristics and applications of salient pole rotor, it has a large number of poles. It is not suitable for high-speed operations due to its high windage losses at high speed, so it is used in medium and low-speed synchronous motors, since it has a large diameter and small axial length. The slip rings and the brush assembly is used to provide the electrical connection between the stationary circuit and the rotating part of the machine, as it is used to energize the field winding using the DC source. And next we have non-salient pole rotor or cylindrical rotor. Talking about the construction of salient pole rotor, it is cylindrical in shape, in which it contains the parallel slots to place the rotor windings. The slots are connected in series to the slip rings, which are excited by DC source supply. The non-salient pole is made up of a solid steel material, and it has a very small diameter and very long coaxial length with uniform air gap. The core has slots for field windings that are secured with help of wedges to prevent from pulled out, while the unslotted portion of core becomes the magnetic poles. Talking about the applications and characteristics of non-salient pole rotor, having smaller diameter and longer axial length. It is costlier than salient pole rotor. Also, the rotor design helps in uniform distribution of flux, mechanical strength, and robustness. So these motors are used for high speed. Next, the permanent magnet rotor. In this type, the rotor has the permanent magnets mounted on its surface, and it has no field windings. The magnets mounted on the surface generate the necessary fields without the requirement of an excitation source. Also, these rotors do not have any slip rings or brush assembly. Talking about the disadvantages, it is not self-starting due to its rotor's inertia. Also, it cannot follow the fast revolving RMF. So, variable frequency drive is necessary for its operation. Next, exciter and frame. Exciter is a small generator placed in the rotor which provides the excitation power for excitation. It consists of field winding and armature winding. The field winding is placed in the stator and the armature winding is placed in the rotor of the machine. Frame protects the motor and covers the whole assembly. And so far we have seen the different parts of synchronous motor. Now let's move on and understand the working principle of synchronous motor. The synchronous motor works on the principle of magnetic locking between the stator RMF and the rotor magnetic field. And we know that opposite poles attract each other. Therefore, the RMF poles attracts the opposite rotor poles, generating a rotating motion. Now let's delve deep into the working principle of synchronous motor. The stator and the rotor are the two main parts of synchronous motor. The stator is the stationary part of the motor and rotor is the rotating part. The stator is excited by the three-phase supply and the rotor is excited by DC supply. Excitation is the process of generating a magnetic field by means of electric current. So the main aim of excitation is to convert the stator and the rotor into an electromagnet. The three-phase supply induces the north and south poles on the stator. The three-phase supply is sinusoidal. The polarity of their wave will change after every half cycle, and because of this reason the north and south pole also varies. And we can say that the rotating magnetic field develops on the stator. The magnetic field develops on the rotor because of the DC supply. The polarity of the DC supply becomes fixed and thus the stationary magnetic field develops on the rotor. The term stationary means their north and south pole remains fixed. The speed at which the rotating magnetic field rotates is known as the synchronous speed. The synchronous speed of the motor depends on the frequency of the supply and the number of the poles of a motor. And it is given by n suffix s equals 120 F by P. When the opposite poles of the stator and the rotor face each other, the force of attraction occurs between them. The attraction force develops the torque in an anti-clockwise direction. And we know that torque is a kind of force that moves an object in rotation. And thus the poles of rotor drag towards the poles of stator. After every half cycle, the pole on the stator is reversed. The position of rotor remains the same because of the inertia. The inertia is the tendency of an object to remain fixed in one position. When the like pole of the stator and the rotor face each other, the force of repulsion occurs between them and the torque is developed in clockwise direction. Now let's understand this with the help of the diagram. For simplicity, consider the motor has two poles. In the below diagram, the opposite pole of the stator and the rotor face each other, so the attraction force develops between them. After the half cycle, the poles on the stator reverse. The same pole of the stator and the rotor face each other, and the force of repulsion develops between them. The non-unidirectional torque pulsates the rotor only in one place, and because of this reason, the synchronous motor is not self-starting. So for starting the motor, the rotor is rotated by some external force, and thus the polarity of the rotor is also changed along with the stator. The pole of the stator and the rotor interlock each other and the unidirectional torque is induced in the motor. Then the rotor starts rotating at the speed of the rotating magnetic field, or we can say at synchronous speed. The speed of the motor is fixed and the motor continuously rotates at the synchronous speed. Now let's see the features of synchronous motors. Synchronous motors are not self-starting, as they require some external means to bring their speed close to synchronous speed before they are synchronized. The speed of the synchronous motor is independent of load, that is, its speed only varies with the frequency of input supply. When supply frequency is constant, they behave as a constant speed motor, irrespective of load condition. The variable frequency controller is used to control the speed of the synchronous motor. Also, the synchronous motors can be operated in both lagging and leading power factors. That is, this motor has a unique characteristics of operating under any electrical power factor. Now let's see the starting methods of synchronous motors. The starting of the synchronous motor does not take place on its own. This means the synchronous motor is not self-starting. And it can be started by the following methods. The first method is use of damper winding. Next, using pony motor. And then using the small induction motor. After that, it can be started as a slip ring induction motor. And next, the variable frequency method. Now let's see the starting methods in detail. Damper winding is the most widely used method to start the synchronous motor. A damper winding consists of a heavy copper bars inserted in the slots of the pole faces of the rotor as shown in the figure. These copper bars are short-circuited by end rings at both ends of the rotor. And these short-circuited bars forms a squirrel cage winding. So when a three-phase supply is connected to the stator, the synchronous motor with damper winding will start. It works as a three-phase induction motor. As soon as the motor approaches the synchronous speed, the DC excitation is applied to the field windings. As a result, the rotor of the motor will pull into step with the stator magnetic field. And next, starting with the help of pony motor. In this method, the rotor is brought to the synchronous speed with the help of some external device called pony motor. Pony motor is a small DC shunt motor. It is mechanically coupled to the rotor of the synchronous motor. Once the rotor attains the synchronous speed, the DC excitation to the rotor is switched on. And when the synchronism is established, the pony motor is decoupled. The motor then continues to rotate at synchronous speed. That is, the magnetic locking takes place and the motor now runs as a synchronous motor. After this, the pony motor's DC supply is made off. So the pony motor will not play any role in running condition. So it is used just for the sake of starting the synchronous motor. And next, using the small induction motor. Here the arrangement is similar to that of the previous method. An induction motor is used to give the initial rotation. Once the speed is developed and the poles are magnetically coupled, the induction motor is mechanically decoupled and the motor runs as a synchronous motor at constant speed. Next method is starting as a slip ring induction motor. Here the synchronous motor is made to start as a slip ring induction motor. For that, the rotor winding needs some modifications. The three-phase supply is connected to the rotor by means of changeover switch. Then the motor starts as an induction motor and it runs near the synchronous speed. Then the DC supply is connected. Now it runs as a synchronous motor. This method is not used in practical because of complications in field winding. The damper winding method is the most popular for the starting of the synchronous motor. And finally, we have variable frequency method. And we know that the synchronous speed is directly proportional to the supply frequency. By reducing the supply frequency, we can reduce the speed of the synchronous motor's stator magnetic field. That is, by controlling the speed of the stator magnetic field, you can lock the stator and rotor magnet easily. And this is the basic concept behind the variable frequency starting method. And here we use the variable frequency drives to reduce the supply frequency. The variable frequency drive consists of rectifier, converter, and inverter module. These modules can be used to convert the constant input frequency to any desired output frequency from the fraction to full rated frequency. The variable frequency drive units are also used to control the motor speed to very low value for starting and then rise it up to the desired operating speed for normal running. While operating the synchronous motor lower than the rated speed, its back EMF generated in the motor also lower than the normal. And so far we have seen the starting methods of synchronous motor. Now let's move on and understand the types of synchronous motors. Synchronous motors can be classified into two types based on how the rotor is magnetized. First, non-excited synchronous motor, and secondly we have DC excited synchronous motor. First we will see the non-excited synchronous motor. Here the rotor is made up of steel. At synchronous speed it rotates with the rotating magnetic field of the stator, so it has an almost constant magnetic field through it. The rotor is made up of high retentivity steel such as cobalt steel. The non-excited synchronous motor are available in three designs: hysteresis synchronous motor, reluctant synchronous motor, permanent magnet synchronous motor. The hysteresis motors are single phase motors. Here the rotor is made up of ferromagnetic material and the rotors have high hysteresis loss property, and these rotors are made up of chrome, cobalt steel or alnico. Hysteresis synchronous motor is a self-starting single phase motor that runs at synchronous speed. It has two stator windings, that is main winding and axillary winding, which will generate the stator RMF. The cylindrical rotor starts rotation due to the induced eddy current, that is, it starts like an induction motor. And once it achieves the synchronous speed, the stator RMF locks the rotor into synchronism. A reluctance motor is a type of electric motor that induces non-permanent magnetic poles on the ferromagnetic rotor. And the rotor does not have any windings. It generates torque through the magnetic reluctance. Magnetic reluctance or magnetic resistance is a concept used in analysis of magnetic circuits. It is defined as the ratio of magnetomotive force, that is MMF, to the magnetic flux. It represents the opposition to magnetic flux and depends on the geometry and composition of an object. And it is denoted by R equals F by phi. R is reluctance, F is MMF, and phi is magnetic flux. Coming back to reluctant synchronous motor, these motors work on the principle of reluctance. Under the influence of magnetic field, a ferromagnetic material will move to complete the magnetic circuit where there is minimum reluctance. The magnetic field lines follows the low reluctance path just like current follows the low resistance path. Therefore, a squirrel cage type rotor is used with some teeth removed to form a salient pole as well as a less reluctance path. Here the stator is similar to the hysteresis motor, having main and axillary winding to generate RMF. At startup, the rotor tries to align with the RMF and starts revolving in its direction. But due to rotor inertia, the RMF passes the alignment position and tries again during the next revolution. And therefore the speed gradually increases and eventually reaches the synchronous speed and magnetically locks with the RMF. In permanent magnet synchronous motor, the rotor is made up of permanent magnet that generates a constant magnetic field. Here there is no windings, slip rings and brushes. The rotor field locks with the stator RMF and rotates at synchronous speed. Since they are not self-starting and there is no winding in rotor, so it requires a variable frequency drive to provide the gradual increase in starting speed. Next, the DC excited motor. In DC excited motor, the supply is given to the stator windings from the external DC source. The magnetic field is produced in the stator winding and thus the rotor excitation takes place. This type of motor is made up of lot size, which may be about more than 1 horsepower or 1 kilowatt. It has both stator windings as well as rotor winding. The direct current can be supplied from separate DC source or DC generator connected to the motor shaft. They can have either cylindrical rotors or salient pole rotors. And it is not self-starting and need damper windings to start. Initially they start as an induction motor and later attain the synchronous speed. Next up, let's see the advantages and disadvantages of synchronous motor. Talking about the advantages of synchronous motor, it has the ability to control the power factor. There is an overexcited synchronous motor has leading power factor and it is operated in parallel to the induction motors, thereby improving the system power factor. Next, the speed remains constant irrespective of the loads in the synchronous motor. And this quality helps in the industrial machines where the constant speed is required irrespective of the load. And these motors have higher efficiency compared to the induction motor and also cost effective. In synchronous motors, the electromagnetic power varies linearly with the voltage. And it can operate in lagging and leading power factor by increasing the field excitation. Next, the disadvantages of synchronous motor. And we know that synchronous motors are not self-starting motors, therefore it requires an external source of DC excitation. Its torque is zero, therefore it cannot be started when there is a load. Also, it cannot be used in an application where frequent starting is required. So when the load is beyond its capability, the rotor and the stator lost their synchronism and the motor abruptly stops. The initial cost is very high and it cannot be used for variable speed jobs. The slip rings and the brushes are required, which results in high maintenance cost. And next we have the applications of synchronous motor. First, the power factor correction. The over-excited synchronous motor work as a synchronous condenser or used for improvement of power factor of industrial loads having lagging power factors. So by changing the excitation of synchronous motor, the power factor of the electric circuit can be varied. And that kind of synchronous motor that is specifically used to improve the power factor is called the synchronous condenser. And next, the constant speed applications. The synchronous motors provides the constant speed at high efficiency so that they can be used for constant speed applications such as centrifugal pumps, blowers, motor generator sets, line shafts, synchronous clocks, text mills, paper mills, cement mills, etc. That is, they are used in constant speed applications where speed does not vary with increasing load. However, the variable frequency drive is used to adjust the speed according to the requirements. And next, the frequency changer. A synchronous motor can be used to drive another alternator to generate supply at different frequencies due to its constant speed nature. So in this case, it is called frequency changer. And it is used for improving the voltage regulation of long transmission lines. A synchronous motor with a field regulator can be used to control the voltage at the end of the long transmission lines by varying its excitation. Using very low frequency synchronous motor, it can be used for very low speed applications with high efficiency. Due to constant speed, they are used for precise positioning in robotics just like servo motors. And finally, the general applications. And these synchronous motors are widely used where the constant speed is needed. In addition to above applications, it can be used in grinders, steel mills, cement mills, centrifugal pumps, clocks, timers, blowers, etc. And that's all for this session. Thank you so much for watching.